I appreciate being here. Big thanks to the organizers for inviting me. So I'm Zahar, or Zach, computer vision engineer at the Center of Financial Technologies, where I've been working for about 3 years now. The company mainly provides financial services, including various deep learning solutions for the banking industry, and covers nearly 100 countries. I've been using Toloka for a while now, gathering data sets for company inner computer vision projects. So today we're gonna cover the following topics. First, I will introduce what's the face antispoofing itself, and then I just specifics of running such a project on Toloka. So after that, I will shortly describe multimodal neural networks and specifically the clip model that I use for image validation for the antispoofing project. So then next I will show the pipeline and what's behind the Toloka UI, so you can expect and how it looks for the ongoing project. So then after I will tell about my experiments with clip for task validation and aggregation. And we will talk about the pros and cons of using such models for data validation and labeling. So then after I'll tell about my actual experiments with vision language models for different computer vision problems. So what exactly is face antispoofing? First, generally it's an algorithm that can recognize real and spoof faces in order to prevent some fraudulent activity, for example, on face recognition systems. It could be many types of visual spoofing, but in this talk, we'll consider most popular and easy to make ones. So that is printed attack. One user trying to spoof by showing printed photo of oneself. And the next popular way is to use replay. Make the video of oneself and show it to web or smartphone camera. Another way is to use a silicon or printed mask. Okay, so the most popular is the printed photo, or just using the photo on the smartphone. Okay. So shortly, we are trying to gather different video pairs. That includes one spoofing video and one real selfie video. We ask performers to make a good quality, real short video, roughly about 3-11 seconds in duration. Also, we ask to make the video of printed photo. And here you can see some requirements, where important parts is printed photo should be real photo of performer, and it should be large enough, clearly visible, and not occluded with anything. We accept a task from different performers from different countries, and now we have probably 60,000 unique performers and from about 50 countries. We're trying to cover many conditions that are specific to the project purpose, like different faces, different background environments, and others sometimes subtle nuances like displays, the types of printed photos, etc. So now let me briefly jump into the concept of multimodal modality in deep learning. So it will help us understand the pipeline. So the key idea is that multimodality could have different meaning, right? We will consider modality as in case of sensoric system. So it could be any of this, like auditory, visual, and even haptic, or any health data. Right. But in our case, it's just simply visual textual model. And we will mainly discuss clip released by OpenAI is in January this year. But also, let's have a look on some important concept to gain an intuition about clip. So here are some related papers from foundational work to most novel. And seam clear and convert is kind of foundational work that shaped the general approach to contrastive learning. And then clip, align, and seam lam. It's the methods that are heavily based on seam clear and convert ideas. And the differences is backbones, data set sizes, and some tricks and optimization for handling large batches or multi-GPU or TPU settings. So for aligned backbones, it's a BERT and FNet. It requires about 1024 TPU cores and 1.8 billion noisy text image pairs. And for CLEAP, at the other hand, they utilize GPT family language encoder and vision transformer or ResNet with attention models. And dataset was about 400 million image text pairs, and training times is 256 GPUs for 2 weeks. And then UFO, and it's a paper described new architecture. It's the unified transformer model for handling language and text by using common encoder. WILD is the CLEAP plus faster CNN for detection. So that's a recent paper. And Philip and Basic and Florence, the most recent works, actually November this year. Florence is a way to create multitask model for computer vision that could be applied to many computer vision problems. And Philip is fine-tuned approach to training large visual language models. And here's there's actually a lot of other works on this area, including audio clip that includes the audio head and Russian version of clip, and also Lemon. So the basic is the recent work from Google claiming about 10% improvement over clip for a bunch of computer vision tasks. So contrastive loss is one of the main takeaways of this approach. So basically the key idea here is to compare how similar two pairs of images are, or image and text. Same class means similar embeddings, and different class for dissimilar embeddings in the same vector space. So yeah, so the clip is a model that allows the similarity assignment between visual and textual representations. It's actually a modified version of convert paper. Concept of using zero shot in computer vision. So method could be briefly explained in the following ways. It has associated image text pairs, as you see here, and the authors do the data augmentation for image part. And there's like image encoder and text encoder. They use ResNet and visual transformer for vision part. And for the text encoder, the basis Phosphania transformer was a certain modification for GPT family. And once you have this set up, you do the following. You take this sequence and you just encode it by passing through this transformer, and whatever comes out from the last layer of the transformer, that's the representation that's going to be used. And just do this simple layer normalization here and projecting this using linear projection layer into the embedding space. So, and then we're here. And T1 to Tn is just the size of the batch. This is encoding we get for the text sequences. So on the other hand, the encoder vision encoder operated send forward. You basically feed through the image and you get the certain representation in the output. In case of ResNet, they take representation after average pooling and do linear projection. So you finally inside this contrastive embedding space. Once we're here on the high level, we want to make sure that image 1 has the highest cosine similarity with the text embedding vector T1. And you want to push all of this in a row to 0. You want to do the same things along the column. So I2, T1 should go to 0. And then just repeat all of this across the batch. So overall, the clips allows to compare image and text. So, and then the advantages is quite versatile on computer vision task. The authors covers like nearly 30 tasks. The disadvantages is the relatively low accuracy for zero shot. And there's like some nuances of training, like it's not for pass to color and size, because after us they used to mainly the resize and cropping, and it's required the prompt engineering required. So now let's take a look at our pipeline. So in the basis, it consists of two main parts. First is Toloka itself is the project and assignments. So performer is asked to upload the video that satisfies some criteria like presence of face, the area, lighting conditions, etc. Then uploaded video goes to backend. Then we cut the frames out of video so we can work with the images. And the next, the image is sent to algorithm that checking the basic requirements, like being satisfied. These checks include presence of a face, the area it occupies. Also, we can rotate and check basic light conditions and find some duplicates. Neural networks that they use here could be generic, like quality, duplicates or rotation model, so generic. And as well as networks that are specific to the project. For example, in this project, we used the face detector, like retina. And here, see the example video. So it should not pass some checks, the quality check, because it's too dark and it has a light spot at the same time. So next, we send a response if task is rejected on this stage. So the video will not flow any further. So then on the next stage of validation, it's more like a refinement stage. We can further detect some anomalies. For example, is there like a watermark, or maybe TikTok watermark, also as there are glasses on the image, or there is a mask on the image, or something like face included by fingers. There could be many scenarios. So you cannot check by just classifier. So maybe there's like visible play or stop button or video player, maybe child on the image, or maybe the Pikachu in the image. There are multiple people, etc. So here things are becoming a bit more interesting. So next, image flows to a bunch of models. So let's call them voters. In our case, these models could be used for detect faces, different video overlays, mask heads, etc. Or in this example, it can detect Pikachu that successfully passed the previous checks by face detector and other quality models. So here I used the attention masks from a few different clip models and then weight them. So consider this for neural networks as voters. And instead of asking them directly, we collect their activation on specific layer and weight the areas of these activations. Also, we can add the weights to every voter and combine them with human voters. So therefore, we can mitigate more effectively possible individual model faults, and we can simulate the aggregation process like a majority vote. So here you can see the activation. So here's another example, and the text prompt was the TikTok text on the image, and two models didn't respond, and two are kind of mixed. So sometimes they fail to answer. And so to visualize which parts of the image activate for a given caption, we use the caption as a target label, and then backprop for the network using the image as the input. So the GradCam. And here's the simplified pseudocode of the pipeline. I used Toloka kit library to handle Toloka API. So the program is checking that Toloka pool is actually open, and then the load attachment that you new. So the basic validation. So as I mentioned before, like doing simple checks and detect face and area it occupies. And after, based on the status of task, clip models with different weights applied, and after photos flow for human validation. So I will release this pipeline so in Jupyter Notebook. So the first my approach was using clip as a ranking model. So basically the clip it is the ranking model. I applied it to different projects like not antispoofing. Here's the credit card detection. Originally, clip accept text embeddings as input, but it can be tweaked to work with image embeddings as input, or a mixture of text and image embeddings. So actually, I tried different ways to get the most from the model during inference. So then I found the way it's better to stack text embeddings described in a line paper, and it works not so good with the same modality like image to image or text to text. It's better with the cross modality, and also you can stack the different text embeddings together. Like in this paper, they've stacked 63 synonyms, and so you can see here you can find like cats on this credit card and the fingers, and you can like filter out some trash of the data set. So I also tried to apply like this clip for different problems, not just classification. Here's the example with the interactive segmentation. The interactive segmentation is the segmentation model plus it accepts some positive clicks from the human. But instead of human input, I used the also activation from clip and or a batch of clip models, and then convert these activations to coordinates, and then pass to segmentation, this interactive segmentation model, helping this model to segment, to label the class. It does work. Sometimes it requires more accurate positive click, I think. And actually, here is the recent work from Microsoft where clip model is applied for detection. And I will share the link with the presentation. So kind of recap, here's like, you can get like about 70-75% accuracy. So it's the same maybe that authors described in the paper. Although I didn't test the exhaustively because it requires some more samples than I have. And it's still project is ongoing. But what I found is you need to carefully anyway prompt engineer. So otherwise results could be brittle, especially for one model. That's because I tried to use some different approach and try to stack model or ensemble them. So ensemble possibly could provide more stable results. And the next is probably it would be these models would be better, and as new models and weights will be released, like as in case in basic approach. And overall, for now, it's expensive to train by average researcher this model. Okay, so that's basically all. And I will share with you the links I used to prepare this report, and also I'm preparing some couple Jupyter notebooks with the pipeline and these clip models. Thank you for listening, and please ask your questions. I would be glad to answer. And you can reach me as well on the Telegram.